And so then I took this one in 2021. This was at 11 a.m. in the morning, okay? So the street lights were on, you couldn't see, and I was an undergrad in 2011 in the drought in West Texas, and we had similar storms to this. And I was really fortunate that I was taking chemistry at the time, because I always had my chemistry goggles in my backpack, because I could walk around with my chemistry goggles to keep the dust out of my eyes. And so I say this not to say that we're not doing a good job at controlling wind erosion in West Texas, because we've reduced wind erosion in Lubbock and the surrounding counties by 80% since 1930. So since the Dust Bowl, we have stopped wind erosion by 80%. But in extreme years, both good and bad years, we still have rain events like this. 2019, this picture here, this was taken after one of our wettest springs that we had in West Texas on record, right? So even in a wet spring, we have dust storms. Even in a dry spring, we also have dust storms. And for us, that's where it comes into understanding the benefits of cover crops. And so for us, cover crops are not about controlling weeds. They're not about improving moisture or improving organic matter. It is purely the physical benefit of keeping the soil covered so it doesn't blow. Unfortunately, it's really hard for me to get my producers to adopt those same conservation practices. So this is a figure taken from the 2017 Census of Agriculture. There should be an update this year, so I'm hoping to have some better data. But this is looking at cover crop or reduced tillage adoption across the region. And as you can see that even in Lubbock, we're sitting around 5 to 10% cover crop adoption, right? And so in our biggest cotton producing counties, there's very little. Also, there's a lot of counties that don't even have any data because people aren't reporting what's going on there. And so I will encourage you all, as you talk to people, please encourage them to fill out the Census of Agriculture. Sometimes it's the only good data that we have in the communities that we're working in. But I just want to highlight this as just to show how little of these practices that we can benefit from a wind erosion reduction practices are even being implemented in our area. Also to note, so I should have included all of Oklahoma. This figure was designed for a regenerative agriculture grant that we ended up receiving that focuses on regenerative practices for cotton production in this area. All three of our hosts today from Oklahoma State are a part of this project. And I talked about this yesterday, but it also just makes it a challenge in cotton production to get that cover crop implemented and up and survive our first freeze here in November or sometimes even in December before we have to terminate it per our recommendations from NRCS. So it makes it a challenge for us to implement these practices in West Texas. And so if I can take you back to your intro soils class for a second, one of the things that we struggle with cover crops is understanding the mineralization and immobilization timeline. And so a cover crop is primarily what two things? Chemically. Anybody want to throw out an answer? All right, it's a little early, but it's mostly carbon, right? And so when you add carbon to a system, you have to balance that with a certain amount of nitrogen, or else you're going to get immobilization. And so for us, it's about trying to determine at what point is that cover crop going to serve as an organic nitrogen source and or inorganic nitrogen source. And we want both. We want the balance between those two systems because it allows our microbes to be fed and then our plants to be fed as well. And so what we're focusing on is mineralization, which is the conversion of organic nitrogen to inorganic nitrogen that's plant available. And then immobilization is the conversion of that inorganic form back to an organic form that's not available for plants to take up. Now there is some work that's being done that suggests that plants can take up small amounts of organic nitrogen, but that hasn't really been proven in the broad scale of things. So we're going to again focus on the two inorganic forms of nitrogen that plants can use, nitrate and ammonium. And what happens is when you have different forms of biomass in the field, based on that C to N ratio, a certain amount of that is either going to be immobilized or mineralized. And so it's important for us to understand at what point we terminate our cover crop to allow that to happen. What complicates this and what the data is showing moving forward is that it's not just necessarily the C to N ratio or the amount of carbons or nitrogens in that plant material, but it's actually the structural composition of those carbons. So is that carbon in cellulose, hemicellulose, or lignin. And what we see is that most of our biomass is showing at like 13:1 C to N ratio, which should mineralize very quickly. But because we have primarily stalks in our cover crops when we terminate them, that's lignin. And those lignins are very slow to decompose in the field. And so how does this work out practically? So this was a study that was conducted in Ag Cares, and it was published in 2004, but it's work from 1998 to 2001, and it looked at, in a conservation tillage system, or it was essentially no-till, but they had to do a few early tillage practices with a cover crop relative to conventional tillage. And what it showed is that with conventional tillage, the optimum nitrogen rate was 35 pounds of nitrogen per acre for a bale of cotton, or for 2 bale cotton. And then for conservation tillage, it was actually 30 pounds more, right? So 30 pounds more nitrogen was needed following that cover crop to achieve the same cotton lint yield relative to a conventionally tilled system. And so, like all good researchers, we took exactly what had been done before and we just decided to do it better with new tools. And so this is a similar system that we looked at yesterday, comparing 3 continuous cotton systems. So conventional tillage, winter fallow, no tillage with a rye cover, and then no tillage with the mixed species cover. Now this is usually when I would be at a different meeting and a different crowd, but I would make my joke about the really expensive rye cover. And so you've already heard that one. But remember, we did include some legumes in that system, and we had hoped that that could offset some of that nitrogen mineralization, or that nitrogen immobilization. And what's also important to note is we only planted that cover at 40 pounds to the acre. Some recent research has shown that you can drop that down to even 20 pounds in our systems to the acre and get the same benefit as having a 40-pound seeding rate. And then we soil sampled at multiple depths just to compare, which will come up here in a second. So yesterday I briefly highlighted this, but wanted to talk about our herbage mass production. Since that's going to be the focus of today, we'll spend a little bit more time on this slide. Just note that in all but 1 year, the no-till rye outperformed the no-till mixed, and that was just based on the seeding rate essentially of those systems. The year that it did not perform well, we thought that it would be a good idea to buy our mixed species cover from a different company, and we ended up not getting Elbon rye, we ended up getting like a tillering rye, and it just did terribly, it very poorly grew, so it's just not a good year for that one. But what I want to highlight too is when we look at stability analysis, and we talked about this yesterday, about if it's greater than 1, that slope of that line, it's going to be a more stable system. If it's less than 1, it's going to be a less stable system. So with rye, our rye is a more consistent performer for us, and we just think it's because of that seeding rate, that a little bit more of it planted means a little bit better stands in these systems. And it does relate back to yield, right? And so we do see a yield reduction in a few years following a cover crop relative to the conventionally tilled system. And yesterday we focused on the fact that we didn't think that it was water, because while we do have these periods where the cover crop significantly reduces the amount of soil moisture in our system, following that cover crop termination, we see a significant increase in water storage capacity, and that remains throughout the rest of the growing season. And we see that in each of the years that we produce this crop. So if it's not necessarily water, or water is not the most important factor for what's limiting yield in these systems, what else could it be? And so we settled on nutrient decomposition and nitrogen availability. So to do this, it gets really complicated. You actually just cut the biomass out of the field, you put it in these little litter bags. So the screen mesh on these litter bags prohibits insects and mites from getting inside of it, but it allows oxygen and microbes to move through. So it essentially simulates what microbial decomposition of these residues would be in the field. So I cut it, took it back to the lab that night, weighed out what it was, and then to a field scale, so our bags were 15 centimeters by 20 centimeters, so I calculated how much biomass in the field was growing in that same area, took a representative sample of biomass, put it in the bags, sealed the bags with a heat sealer, and then I tethered them with these nails in the field to simulate what surface level decomposition would be. Now, there's going to be a few critics in the room that said I should have buried my litter bag so that way I could simulate microbial interactions, but remember this is a no-till system, and so we're not going to introduce that cover crop into the soil solution itself. And so it's important for us to represent what is the slowest or the most microbial rate of decomposition. And then I retrieve these litter bags at set periods throughout the growing season. They were great in theory. They're very expensive. They're like $15 a bag. And then I have a farm manager who I'm pretty sure despises any research trial that I come up with. And in a no-till system, he managed to hit them with a plow. I don't know how that works. But anyway, so I was able to recover enough to statistically significant, but I went from 12 litter bags per sample collection to 6 litter bags per sample collection because of the plowing event. And then I collected soil samples directly beneath the litter bags to simulate what is going on in the soil community following that collection. All right, so we're going to talk about cover crop decomposition, all right? And so I have it presented here as remaining biomass throughout the year, and this is days after cover crop termination. The gray line is going to represent when we planted cotton. So imagine this is how much biomass was remaining at cotton planting date. 2020, we had lots of biomass. 2021, we did not have as much biomass. And look at the differences in decomposition rate between 2 years. So in 2020, at cotton planting, we still had 90% of the biomass remaining in the field at cotton planting. That's 8 weeks after cover crop termination. 8 weeks, and we still had 90% of the biomass remaining. Now, keep that number in mind. We only decomposed 10% at cotton planting, okay? Then we fast forward to 2021, and at cotton planting, and this is also 2021 was a weird year. No one should plant cotton 90 days after cover crop termination. We have this thing in West Texas pretty frequently called inland hurricanes. Has anyone ever heard of one of those? And so it's essentially a micro downburst where we had 175 mile per hour winds that drop down in like a half-mile area. And so it's essentially called an inland hurricane. Wiped out our cotton crop in mid-June. I replanted cotton on July 4th because I had to have something to defend for my dissertation. And so normally I would not recommend planting cotton in West Texas on July 7th, but for research purposes, I needed to graduate. And so anyway, that's what this line represents as a really late planting date. So if we look back at about 50 days, we were still at around 35%, and we didn't decompose much more after that. Now, what I want to note is 128 days after cover crop termination is about peak nutrient uptake for us in West Texas for our cotton crops, and we're still here at 80% undecomposed, okay? And here, we're looking at the same time frame. We had decomposed all but about 30%. And so those numbers are important when we go here. And we talk about the nutrients that can be released from that. And so this is a theoretical amount of nitrogen that can be released following cover crop termination using just C to N ratios. So we're going to focus on 2020 because it was actually a good year. But essentially, this is how much biomass we produce. So a little over 4,000 pounds to the acre of dry matter. So that's a good cover crop, right? That's really good for us in West Texas. And at a percent nitrogen of 3, essentially, we could have mineralized 128 pounds of nitrogen. What is a yield goal for cotton production in Oklahoma? Let's not talk about Altus because they can produce all kinds of crazy numbers. But in a dryland cotton situation, what is the yield goal here? 2 bale to the acre, bale and a half? And so you would have more than enough nitrogen in 2020 just from your cover crop decomposing to produce a 2 bale cotton crop, even a 3 bale cotton crop in West Texas, if you got all of your nitrogen just from the cover. Unfortunately, we have to look at how much of that nitrogen is actually going to be released during the growing season. And remember back here, when we're looking at our decomposition rate at cotton planting, we're only at about 85% decomposed. So even at the best of times, we're looking at around 20 pounds of nitrogen that's going to be released from that cover crop at cotton planting. So what's happening is microbes are tying up the nitrogen in that cover crop or any nitrogen that we add to the system, and it's limiting our cotton production in West Texas, especially early on. And one of the things that I asked Brian about yesterday is our work in West Texas shows that modern cotton varieties take up less nitrogen, but they take it up about 3 weeks earlier than their historical counterparts. And so our nutrient recommendations, if you're not shifting your fertilizing practice earlier in the season, especially following a cover crop, you're not going to be able to balance the nitrogen that those plants need. Now, can anyone foresee a risk associated with putting your nitrogen on earlier in a season when we have really rough climatic events, right? So there's a risk that the producer has to take early on in the growing season, I'm going to show you that risk here in a second, of you may not produce a crop, but you've still already invested in nitrogen in that system to try to offset following a cover crop. Okay. So then looking forward, so these are some soil samples we collected. This is looking at soil proteins. I'm not going to bore you with the chemistry of this, but essentially proteins are organic nitrogen sources in soil, and then also our inorganic nitrogen fractions. What's interesting to note is so this number right here, you see the spike shortly after decomposition. This is that mineralization of nitrogen. So these are microbes that are releasing nitrogen back into the system. And then subsequently at our next sampling point, we see an increase in inorganic nitrogen. So we're actually seeing this mineralization and immobilization happening in the field. Now, one of the deficits of my system is we fertigate our nitrogen over the top of the entire system through the pivot. And so after about 50 days, I couldn't see any differences because on day 52, they put about 35 pounds of nitrogen out just through the pivot. So I can't tell what the nitrogen dynamics were in my system just from a soil perspective because we had an increase in the amount of nitrogen fertilization. But what's important to note is that proteins can help us track this mineralization immobilization time frame. All right, and then the economics, I got this question yesterday, does it pay? So this is looking from 2015 to 2017. The results are almost identical in 2018 through 2020. What we see is that numerically the continuous cotton conventional till system does yield greater gross margin for us, so more money per acre. However, there's no significant difference. So out of 8 years, there was no significant difference in these systems. However, the conventionally tilled system regularly produced more cotton or better cotton, I would say, on average. And this does use the loan value as that calculation for economics. So those are small plots, right? 16 rows wide, 200 feet long. There's some deficit in using small plot research, especially for economics. So we wanted to look at cropping system scale size, so using an entire pivot span. What would we look at for the same idea? And we took the results from the study that we had with the cover crops and designed this system where we wanted to take that nitrogen fertilization period and optimize it for cotton production following a cover crop. And so in Texas, right now, our fertilizer recommendation is that if you're going to follow a cover crop, you add an extra shot of nitrogen at pinhead square, okay? And so for us, we thought that that was a little bit too late, so getting a little bit late in the growing season, especially following a cover crop. So we designed this system to where we worked in three areas. So the continuous cotton winter fallow, so business as usual, our continuous cotton rye cover crop system, and then a cotton wheat fallow rotation where 1 year would always have cotton on one of the wedges. And then we compared that to 4 different fertilization practices. The farmer's practice, which is 120 pounds of nitrogen per acre. And then because it was fertigated at the time, we couldn't optimize the system, so we added the 30 pounds of nitrogen. So that comes up into the cost. But essentially, we added 30 pounds either pre-plant, so 2 weeks before planting, 3 weeks after post-emergence, or pinhead square plus 2 weeks, which is the current extension recommendation in Texas. So either 120 pounds or 150 pounds at different timings. And so these are the results for that. And so it's a little bit of a busy figure, but essentially we have our systems that are running horizontally. So our continuous cotton system, business as usual, our cover crop system here, and then our cotton wheat fallow rotation. And then running vertically, we have our different nitrogen fertilization practices. So our farmer's practice, our pre-plant nitrogen, our post-emergence, and then our pinhead square. And what we see is that following a cover crop, you see the added benefit of adding that nitrogen earlier in the growing season than later in the season. So that pinhead square application is too late for us compared back to a conventionally tilled system. However, what's interesting to note is with the cotton wheat fallow rotation, you don't see an added benefit of additional nitrogen. Anyone have a guess as to why? Essentially what's happening is we had 11 months for that cover crop to that wheat residue to decompose, and so we don't need the extra nitrogen to offset the microbes in that system. They've had plenty of time to balance out. But also what I want to note is on average, we are seeing a 23 and a 50% increase in cotton lint yield with our conservation systems relative to our conventionally tilled system if you optimize the system for nitrogen management, right? And so then we're going to talk dollars and cents. Okay, so this is gross margin, same figure again, but we're just looking at the amount of money you can make per acre. And notice with that cotton wheat fallow rotation, you can see a 77% increase in gross margin for that system, and with a cover crop, a 65% gross margin. And that's assuming all of the input costs are the same, except when you defer based on the system. And so what's important to note, though, is yes, you may make 77% more, but with wheat prices in West Texas, and we don't have a grain elevator anymore in Lamesa, there's nowhere to transport your grain to. So you don't make any money off of your wheat crop, or very limited amount of money off of that wheat crop. And then you have a fallow period where you're not making any money. So yesterday I mentioned one of the things that we're doing with partnership in Dawson County is we're trying to set up a system of tax deferment options where producers can enroll in this program. They make that 77% theoretical increase in gross margins, but they only pay taxes on their land every third year, only in the year that they have a cotton crop, with the goal of kind of the county supplementing some of these conservation adoption practices, especially for water management. Any questions on any of that? Okay. Clicker is not liking me this morning. Okay. All right, so then, so that was 2018 to 2020. In 2022, I'm sorry, 2018 to 2022. In 2022, we changed the system up. So remember, we were fertigating that nitrogen, and we got a lot of complaints that like, well, you're adding 30 pounds of nitrogen, no wonder why you're yielding more, your cotton needs more. We don't agree with that, but so we optimized the system again, we turned off fertigation for these systems, and so we're knifing in this nitrogen now, and we split it up to where instead of 120 pounds, it's going to be 90 pounds total, but split up at different time frames where we add a little bit more up front or a little bit more later in the growing season, and wanted to see what that looks like. Now again, I apologize for these figures. I made a report and then I didn't leave myself enough time to make it pretty before I came to this meeting, so shame on me. But this is directly out of the report, and what we're seeing is that same trend where essentially if you optimize for the nitrogen in the system, you see an increase in yield, except in 2023, where we did see a significant reduction with that rye cover. We've had 2 really bad years in West Texas. If you can note, cotton yields, I mean, those are terrible yields, right? Like most people would not even harvest that. We are harvesting that because it's a research trial and we need data. But essentially, we are seeing a reduction in 2023 with that rye cover crop system compared back to the conventionally tilled system. All right, so in summary, cover crops biomass decomposition does depend on the herbage mass production, so the amount of above ground that you have, as well as your environmental conditions to decompose that cover crop later. The herbage mass can immobilize soil nitrogen earlier in the growing season. However, supplemental nitrogen fertilization can offset that immobilization. So our new recommendations that should come out January 1 is following a cover crop, you need to add 30 pounds of nitrogen, and you're going to apply that either pre-plant or post-emergence. The post-emergence is a better option for most of our producers from a risk standpoint. And then also we're changing our state recommendations. It's currently 40 pounds of nitrogen per bale. We're dropping that down to 30 pounds of nitrogen for the first bale, and then 35 for every subsequent bale after that. But also a cotton wheat fallow rotation may be a better alternative to cover crops in certain places, especially our sandy soils in West Texas. So with that, I'm welcome to any questions you might have. Went a little bit fast, I think, but not as bad as yesterday. Yes, sir.
I think that above ground growth is about
Great question. So we looked at above ground biomass. Did you look at below ground? So we did, not in this system, but in another system. So we essentially calibrated, so we wanted to see what is the ratio of above ground biomass to below ground biomass, so that way we didn't have to dig up a lot of our no-till plots. And what we found, it's about 2 to 1, so double the amount of biomass above ground as below ground. The issue that we're running in, say again? For the rye and the mix, yes, sir. And essentially it's just because we're only getting rye in our mixed species cover anyway, and so there's very little going on. Or there's very little difference between the two of those. What I will say though is when we have more favorable spring rains, we're getting more robust root growth than when we get these little spitting rains that we've been getting, kind of a consistent trend in our wintertime. And who knows, this winter's proving to be a little bit wetter than the last two, but it needs to rain again for us to get some really good herbage mass growth. Good question. Yes, sir.
On the cover crop, are you also working with a weed scientist for future problems of weeds in the next crop? You know, not arguing the other side of it, but future weeds, you had hairy vetch in one of them. If all those seeds don't sprout that one year, you've got 10 years of hairy vetch seed you're going to be fighting.
Yep, very good point.
So are you doing work to see the effect of remnants of the cover crop in future crops?
Yes, so great question. So are we working with weed scientists to kind of optimize the system from a weeds dynamic, or at least to understand the weed dynamics? Yep, for future planning. So I know my title says Cropping Systems Agronomy. There's an amperstamp that's supposed to come after that, and I have a weed science appointment. It's probably the worst weed science decision that Texas A&M has ever made, because I've never taken a weed science class in my life. But I did have a weed scientist on my Ph.D. committee, and so we did do some weed population studies. One of the things that we found in our system is that we had increased weed pressure. So, these systems were started in 1998, so no tillage since 1998. We have a little bit of a compaction issue in our no-till systems, and we also have had some increased weed pressure, especially resistant Palmer amaranth that is in these plots now. And so one of the things that we implemented in 2020, was we came in and we did a very shallow tillage event right at like the seedling emergence of some of those Palmer amaranth. And what we found is we saw an 80% reduction in weed pressure in season with those systems, which was nice because I used all of my favors to get student assistants to help me hoe these. But also, we didn't see any reduction in soil carbon storage because our carbon storage starts at about 6 inches below the soil surface. So we can do very limited plowing in these systems, control the weeds, and also still sequester the carbon and see the benefits of kind of breaking up that plow pan on the soil surface. Well, I guess not plow pan, but a no-till pan. So yeah, we are looking at that. Our hairy vetch hardly ever germinates in West Texas, so we've been fortunate. We did have a study in Brownfield, so about 45 minutes from here, and it was 100% hairy vetch fields. It was on farmer site, and I think the only reason that we didn't get beat up by the farmer, because there was a lot of hairy vetch issues now, is because it's Katie Lewis's husband was the farmer cooperator that we worked with. So, and she brings home the bacon, so he couldn't get too upset with her about that. But yeah, it's a big issue that we're having. Sweet clovers are being introduced in the area, and they reseed really well. And so we've had issues with sweet clovers coming up in the springtime and then having issues planting into sweet clover residue. So it's something that we're looking at and trying to optimize our cover crops for this semi-arid system. But I would say by and large, most of our producers are using some kind of grass in the system, rye, oats, or wheat, and even some barley now. Yeah, great question. Other questions? Yes, sir. So we have not ever fertilized our cover crop. You know Wayne Keeling. So Wayne, the guy who I replaced for this position, is the most old school researcher you will ever have. And his philosophy, because he's tenured, is if it doesn't work, it doesn't work, and you have to publish it doesn't work. Now, for those of us who are young research, I have to have something to publish, right? So we have not fertilized our cover crop. We don't irrigate our cover crops. It is you plant it and you see what happens to it. There is some work, I think y'all did it, right, where you fertilize cover crops to see how they would do. And I think they performed relatively well, but sometimes you can get a spurt of growth in it, and then it kind of offsets the benefit of that added nitrogen to the system. Yeah.
Any other questions, Dr. Burke? Oh, we got one here.
Yes, sir.
We have seen this problem in Brazil with no tillage, so especially in the beginning, optimization, ironing, mineral depletion. How long do you think has been carried out? And do you think at some point will be some this nitrogen will come back?
Yeah, so the question is, how long has no tillage been going on, and do we think that will help, eventually will that nitrogen be cycling in the system enough that it won't be tied up? So great question. So no tillage was implemented in 1998, and so these results from this system were years 18 through 22 that I showed today. And so it's a pretty long time to start to see that nutrient cycling. So we have not seen that the system is self-sustaining yet. Our projections, one model showed that it was 71 years before we would get to the nutrient cycling where it could sustain itself. Another model showed that it was like 33 years. I will not still be working these plots in 71, whenever we hit year 71. I hope to be retired by then. But I think the issue is that you have good years and bad years for water, and I think it's water is the primary factor when it comes to nitrogen cycling and not necessarily the amount of organic or inorganic nitrogen that's in the system. We haven't seen leaching, so we don't think that we're losing nitrogen below ground. Wind erosion is pretty much stopped in the system, so we don't think that we're losing it through soil-blown particles. We really just think that it's the biomass itself that's just remaining in the system. One thing important to note is I didn't show the pictures, but we labeled, like physically went out and tied string around different amounts of biomass and then came back and took pictures of that as it decomposed every 2 weeks throughout the year. And we had some straw in the system from 2020 that is still physically present in the field. And we had to replace the string because the string decomposed faster than the straw did. So in these nitrogen limited systems where you also have a water deficit and it's really dry, that biomass can remain for a long time. So we actually implemented a study this year where we're looking at can you plant a cover crop every other or every third year and still get the same benefit to that system as planting a cover crop every year where it takes forever for it to decompose? So, or maybe not forever, but a long time. So, great question. Other questions? I will be, oh, yes, sir.
In your cover crop cycle, when will be the optimum time to soil sample for the next cotton crop? Is it the beginning of your cover crop, middle, or 2 weeks before you're going to plant cotton, or?
Great question. So when is the right time to soil sample? I'm assuming for fertilizer recommendations following a cover crop. So great question. I wish I had it. I usually have like a deck of slides below when I try to leave anticipated questions. So my master's research was all on temporal dynamics of carbon and nitrogen in these systems. So I went out and sampled monthly in the top 6 inches just to estimate that very question. And the first time I came back with my results, Katie Lewis, who was a new faculty member at the time, said, "You did it wrong, go re-extract them and rerun them." So I went back to the lab and I reran them, got the same results, and she's like, "You're still wrong. Like, what are you doing wrong in the lab? Why are you wasting so much money?" And so she came in the lab with me and did the same test. And the reason why she was confused is we saw a 60% change in carbon and nitrogen storage from 1 month to the next. And it literally looks like a scatter plot. So what we recommended is most of our producers are soil sampling in April for fertilizer recommendations, and we said you keep that time frame. We've already terminated the cover. It's probably been terminated for at least 4 weeks, so leave that as your time frame and use that as your annual fertilizer basis, but then go in and note any amounts of nutrient deficiencies that you see in season. Because if we were asking our producers on to use their consultants primarily to soil sample their conventional fields at one time and then their no-till fields at another, we figured that they would be getting incomplete results. So we wanted to stick to a pretty consistent system. And so we recommend April 15th is still our soil sampling date for all of our systems. But great question. I'm happy to share that paper with anyone too. I will be leaving, so reach out to me via email or send me a text message or something. I have to get back to Texas. But thank you all so much.
Speaker up will be Dr. Steve Phillips hitting again, coming back. This is the wrong slide deck, right? You're not doing Magruder again, are you? Nope. I saw that. It's like, no, I didn't pay you to do it. Same thing. There we go. Fertilizer trends in Oklahoma. So Dr. Phillips.
How's that sound? Is it good? Check. All right. Well, first off, I just want to commend everyone on the prompt arrival this morning. As Brian mentioned, I've been out of the country for a few years, and as an extension specialist outside of the U.S., you have to learn to adapt in your programming. I can't even suggest a 9 o'clock start time in any African country, much less an 8 o'clock. Nobody will be there. I have to schedule it to start at 9, knowing that the dignitary that wants to give the welcome will be there about 9:20 for a 5-minute introduction. It'll take 15 or 20 minutes, and then we'll get going on the program about 10:15. I learned this the hard way. I was doing a program in West Africa, and we had got started again about an hour and a half later than scheduled, and it came time for the break. I said, okay, let's all take a 15-minute break, and one of the administrators raised the hand, said, well, is that 15 American minutes or 15 African minutes? I said, what's the difference? He said, about 15 minutes. So you learn and adapt, but I appreciate everybody being here this morning. This is a topic that has been a personal project of mine since I got here. It was just something that I wanted to do as a bit of self-study. I've been gone for a long time. When I left Oklahoma, we had 30 bushel wheat, 2 bale cotton, and that was pretty much it. And now I come back and we're much more diversified agricultural systems. Lofton's double cropping this and double cropping that. Brian won't even get the combine out of the barn for less than 70 bushel. So I needed to reacquaint myself with Oklahoma agricultural production, soil fertility, the geography of the state, cropping systems. It's just a lot for me to learn. And so I started going through some old data, and I'm going to share some of the things that I've found interesting during this process with you. You guys surely are familiar with the 5-year summaries that Hyland has been putting together. He's been doing this since back in the 90s. The most recent one just came out in 2022. Do you all know about these summaries? Do you look at them when they come out? Who uses the OSU soil testing lab? Show of hands. You sample? Commercial labs? Sending your samples to commercial labs? Okay. Well, these come out every 5 years, so I'm going to talk a little bit about this, but I'm also going to talk about this soil test summary. When I was with IPNI, this is something that we also did every 5 years, and we did this all of North America, so U.S. and Canada. We surveyed all the state labs and the private labs. And so the data I'll show from here will include all of the Servitech, Ward, A&L, now known as Waypoint. All of those Oklahoma samples will be in here as well. So we got 2 sources of soil test data that I'm going to talk about today. The website for this is free. You can go look at some of these charts I'm going to say. This was an IPNI product, as I mentioned. When IPNI disassociated in 2019, TFI, the Fertilizer Institute, took over this tool, and so it's on their website now. I don't know what the future of this summary will be. We had already started, when we shut down in 2019, we had already started this 2020 summary, so we went ahead and finished it off the clock, basically. But I don't know what the future will be, but we've got 5 summaries available on the website. And so we've got 20 years of data to look at. I'm only going to talk about P and K today. pH is a cool thing to talk about in Oklahoma, but I don't really have time to get into it. But if you want to go look at these data, you can see these for Oklahoma: P, K, pH, magnesium, sulfur, zinc, chloride, all available on that website. In terms of number of samples in that survey, you can see we've got about 20 million samples to look at. So in terms of drawing some conclusions about trends, and we talked about this a little yesterday with the challenges of statistics and these disassociated data sets or abnormal data sets. We started at about 2 million samples in that first summary, and then have been running about 7 million on the last 2 summaries. Comparatively, the data from Oklahoma, Hyland has about 50,000 samples in a 5-year summary. And so both he and IPNI remove homeowner samples from those. So these are only agricultural samples that we'll be talking about today. But, you know, quite an extensive database. This is what it would look, this is what it looked like. This is just U.S. potassium trends. And so what we do is when we request these data, we have these predetermined categories that we ask all the labs to submit it in, because, you know, every lab uses different extractants, and so the numbers are different, whether it's malic or bray or ammonium acetate, whether it's a wet K sample or a dry K sample, whether they're analyzing using ICP or colorimetric methods. There's a lot of variation, and so we get it in as they report it, as they collect it, and then we standardize it for the summary. But we ask them to, you know, put it all, basically the percent of the samples. They don't send us raw data unless they don't have time to summarize it, and then we have to do that. But usually they just send us a summary of the percentage of their samples. This would be the 1 year. For example, the 2020 survey is just the 2020 data, whereas comparatively the Oklahoma State is a summary over 5 years. So we get this, and it looks like this, where it'll be a typical distribution around, you know, our agronomic ranges here. And so we can look at, as we have all these data, we want to look at the change over time in the distribution of samples in these different categories. And so what we can do with that is then we can make some conclusion about the trend that's happening. So ideally, we would have some sort of target soil test level. In our case, in sufficiency, we'll say that's around 90 to 100% sufficient, where we expect to not lose yield if we don't fertilize. And so ideally we would see proportion of samples increasing in that target zone, and then draw, as we're building up our lower testing soils and beginning to draw down our higher testing soils, we'd see a shift like that. The converse of that would be where if we're just not fertilizing and we've got things going out, or we're over fertilizing and moving things out of that target zone. So this would be representative of a mismanagement of our fertilizer resources. General trends would include a depletion, where we're just moving through that target zone with fewer samples above that, an increase below, and then of course the converse of that would be an enrichment. We're continually overapplying certain nutrients. So how are we going to define that target zone? Well, this is the general response curve relative soil test value to crop yield. And this is a generalized representation of what most all testing labs are using for their calibration data, for their soil test interpretation, that at certain soil test levels we are very confident that we're going to respond to a fertilizer application. Then we have this zone of, as the curve begins to flatten, where it's more of a 50-50, maybe, maybe not. And we heard a lot about that yesterday, how, you know, it should respond, but it doesn't. We don't expect it to, but it does. A lot of those are within this range. And then we get out here on this plateau part of the curve where we don't really expect to get a response. And so if we look at an example of one of our sufficiency curves, this is for wheat, whereas in sufficiency this would be 40, 60, 80, 90, and 100% sufficient. So we can invert that and transpose it on here, which would make me say, okay, 40, 60, 80% is going to be in here, 90 to 100. So we would say, okay, even at 100% sufficiency, we still are seeing some responses to fertilizer inputs. Brian talked about that a little bit yesterday. But then once we get on out, you know, beyond our index level, that's when we would start coming into the flatter part of this curve. We used to talk about this a lot, especially when we start looking at, when we have farmers that are using the state lab, or they're using a private lab, and they're sending the same sample and they're getting different soil test report, different fertilizer recommendations. And so I used to have to do this talk a lot, explaining soil test philosophies and recommendations and how it all ties in. And so we put together a generalized table. I used 11 different extension services throughout the Southeast, and we worked together to come up with this generalized representation of these soil test categories. Some states will just tell you, well, your test is medium. There'll be no number associated with it. We use sufficiency, some use build maintenance type philosophies. But in general, if we put this in terms of sufficiency, it'd be about 40, 60, 80, 90 to 95, and then 100%. Or even at 100%, there's still a probability that it would respond to a fertilizer application, but we don't really expect to lose yield. We have a very low chance of losing yield if we don't fertilize. And so that's kind of how we used to define target areas for this analysis. So in the case, and so now we're moving into Oklahoma phosphorus data. You can see we've got 150,000 samples or so going into this. What is that number? Oh, my screen's not working today, Brian. About 40,000 samples in the 2020 data. And so in terms of our target range, it would be here, because these are in parts, these are in parts per million. And you know, our state soil test lab comes out with our index, which is basically parts per million times 2 on a 6-inch sample. And so when we're looking at parts per million, this would be our index of 40 to 65, basically, on phosphorus. So 90, 95%, depending on crop, to 100% sufficient. So as you can see, we've got a lot of samples for phosphorus testing below and fewer here. So this seems to suggest, it's hard to see the change looking at these individual bars, which is why we do the next analysis. But just the glance at this, we got a lot of soils testing below that target range in phosphorus, and have had for the last 20 years. So if we look at our critical level of 33 or 65 on the index, you can see a general trend. But what's interesting to note is that even since 2021, our median soil test level has been below the critical level for phosphorus across the state. If we compare critical levels, just out of curiosity, look and see, here we are, 33. We're pretty similar to more to the Mid-South area than we are with the Central Plains. You would tend to think, what state are we most like in terms of our responsiveness to phosphorus fertilizer? We seem to be more in line with the Mid-South here, but you can just see kind of the different critical levels across the nation. And so here's the graph we put together summarizing that chart with all the different colored bars for all the years. What you can see again, there's our target range right there. And so clearly you can see in terms of phosphorus, we're depleting soil phosphorus. We're going down in those higher categories, and we're seeing an increase in the percentage of samples in those lower testing categories. What's concerning is that we're moving right through that target range. We're depleting across and moving right on through, and these are on soils that have been low. And so we're drawing down phosphorus even on soils that were already below the critical level historically. In terms of the summary in 2020 on that IPNI survey, 81% of the samples from Oklahoma tested below that critical level of 33 parts per million or 100% sufficiency. Again, pretty similar to what we see nationally. The color indicates the change in percent of samples from the 2015 to the 2020 survey. So we're here, in that 0 to 10% or 10% change. So we were somewhere around 70% in 2015. It's up to 80% in 2020. We compare that to the state lab summary, which covers the year 18 to 22. So that 2020 data from IPNI falls right in between here. We'd be looking at, the below 40 and the 40 to 65 on our index. So we're at about 76%. So 76%, according to the state lab, are below critical levels over a 5-year period. That single snapshot from 2020, 81%. So they're in agreement. Most of our soils coming in, getting tested, are below the critical level for phosphorus.
Is that calculation available phosphorus or total?
That's extractable phosphorus. That's soil test P. And so here we have the median soil test level, 14. Again, pretty consistent with what we see through the Mid-South. Again, the change, that has dropped in the past 5 years. Compare that to, and one thing that I really like about this state lab survey is they give you the data by county. So we don't have any of that information on the IPNI survey, but if we look at by county, the median for this data is 32. And so, again, remember that's the index. So in parts per million, that's 16. So again, 14 versus 16, we're in good agreement. And so if you look at our distribution statewide, again, remember we're looking for 32 as the median, 65 is 100% sufficient. So you see, we don't see a lot of them. You got 76% of your samples coming in below critical. You're not going to see a lot of 60s. What's most concerning is this little band right over here seems to be the only regional grouping. We're in pretty good shape. At 40, that's 90% sufficient. So we're 80, 90%. But over here, we're starting to push down into that 76 to 80% sufficiency, and that's getting us outside of that questionable response areas to where we would expect to see a response to phosphorus fertilizer in some of these counties here in the eastern part of the state. Another tool that exists that allows me to look at things on a by-county data, by-county scale, is a tool that another one we built when I was at IPNI. It's called NUGIS, the Nutrient Use Geographic Information System. This one is also still available online. TFI hasn't updated it since 2016, but as I'll talk a little later, I think we've got an opportunity to continue this because it's really a pretty useful tool in terms of looking at things spatially. This is what the website looks like. It's a very robust data set where it goes back to 1987 to 2016, and you can look at things either at the county level or by watershed, and you can calculate fertilizer inputs, which is based on APCO sales data. You can look at manure added nutrients, which is based on ag census data, livestock in CAFO with a manure coefficient for the different types of livestock in the different counties, legume nitrogen, crop removal based on ag statistics on planted acres, harvested acres, crop type, again using standardized removal coefficients for each crop. And then we can use these data to calculate nutrient balances and nutrient removal to use ratios. So if we throw up the phosphorus balance map of the United States, you can see it ranges from very dark green where it's greater than 300, which means there's 300 pounds more per acre going out than there is being removed. And again, this map is from 2016, so it's a snapshot of interest, but then we'll look at some trends and see what's happening going forward. But you can see what catches your eyes here in the Mississippi Delta region. Dark red, that's been red like that since I started using this tool in 2009. So we've seen some things happening across the country in terms of nutrient depletion and enrichment. If we zoom in on Oklahoma, you can see it kind of matches what we know, what we've seen from the soil test on phosphorus, that these are depleting. Not too bad, a little more. We've got one county out here, Texas County, where we actually have a surplus of phosphorus. And so if we can drill in 2 individual counties, let's look at Texas County. Let's look at one of those that's being depleted. We'll pick Grant County. And then one that's fairly neutral, I'll pick Custer County for that one. And so just to see what we said, now, I want you to note, this is not the 18 to 22. This is not the most current. I went back 5 years so that these soil test values will match what I'm showing you on those 2016 NUGIS values. And so if we look at these 3 counties that we're going to highlight, you can see again we're in the 40s there. This one's 100% sufficient out in Texas County where we have the surplus, but we'll look and see what these soil test values, how they correlate to what we're seeing on those phosphorus balance numbers. So we'll start first at Texas County, and what this graph represents is the annual calculation of fertilizer input, manure P input, and crop removal. You can see from 87 to 2017, the big source of our balance out there in the Panhandle is the manure application. Now, this is not an exact science, the way we can use these data, because we have to distribute that manure input throughout the county. We don't know exactly where that manure is moving from the CAFO to the farm. We know how much manure is generated in that county. We know how many crop acres there are, but there's really no way to do any more detailed data than that without, ag census type getting on the phone survey stuff. But for this case, clearly what we see is that the big contributor to that phosphorus is the manure. We have seen an increase in fertilizer. We did see an increase in fertilizer P through the latter part of the 20-teens. Crop removal's been pretty consistent over the last 5 years, but that's why we see that surplus out there is largely the animal agriculture. Switching over to Grant County, where we've seen a deficit in P, you can see again fertilizer use has been pretty consistent, but we're getting beginning to get a bit of an upward trend in crop removal. I don't know if this is crop changes, sequence changes, higher yields, could be several factors, but the deficit is being created not because of a reduction in fertilizer use, but because of an increase in crop removal in that county. And the Custer County data, which has been pretty neutral, the data reflect that as well. Pretty consistent crop removal averaged over the last 5 years or so, pretty average fertilizer input values as well. And so if we jump forward now, where we looked at the soil test data, now here's what we have in the current survey. And so, no change at all here. So that makes me think that that trend of neutrality we saw in terms of balancing the inputs to the outputs in that county have remained consistent from 2016 through the present. We've dropped about 5 pounds per acre. This is an index, 5 pounds per acre in Grant. As we talked about, that crop removal was going up, beginning to exceed a steady fertilizer input, and the change in soil tests would reflect that, and really no change out here in the Panhandle. And so these two data sources give us an idea of management practices and changes and how those are affecting the changes we're seeing in these soil test summaries. Switching gears, looking at potassium now, here's the Oklahoma potassium distribution. Our target zone here is down, so not as concerning as the phosphorus in terms of the percentage of samples below that critical level. But again, we've still got some, and we can see if we look at those bars, it seems like they may be trending toward a depletion case, but not nearly as pronounced as the phosphorus. We look at critical levels here. Our critical level for potassium is technically 125 for most crops, a 250 index, but if you put in soybeans and peanuts, that pushes it on out to about 138. Alfalfa will take it out even further, but for this exercise, we've just pushed it on out to 138. But again, see, we started out 20 years ago, well above that critical level, and have gone down over time to we're right at it now, it seems like, in terms of the median soil test for potassium. Again, comparatively, what's interesting is this, as you remember in phosphorus, we seem to be more like our neighbors in the Mid-South, but here we're more Central Plains in terms of potassium. And so that means in terms of the drivers that affect the availability and the uptake mechanisms and the nutrient cycling in the soils, Oklahoma soils tend to behave with regard to phosphorus more like southern soils and more like Central Plains soils with regard to potassium. So here's that same chart, and we do see a little depletion overall, But the difference in the potassium is that we're still increasing in our target range, which we would say is an agronomically sound trend, but I think it's probably just moving its way through. They're still heading because we don't put out much potassium fertilizer, as you'll see on these Nugis graphs. But this one, again, it is what it is. I mean, we're drawing down, but we're still in a little better shape with regard to critical level. Only 40% of the samples are testing below critical level for potassium. Again, pretty comparable, to our surrounding states. Again, we're still minor changes, but we have seen that number go up in the last 5 years. Looking at the state lab samples, again, we got 37. We'd be looking at these two categories for below critical. That's about 54%. So compared to 40, there's a much bigger difference. You remember the phosphorus was very comparable. This is a lot different, that the samples coming into the state, 54% are below critical, but only 40%. I think what's probably happened is these are a bunch of panhandle samples going to Servitec, and so a lot of the higher K testing soils are going to private labs, and so that's why the percentage of samples would be higher in the state lab testing below critical, because they're missing out on a lot of high soil test K samples that are going to private labs in the panhandle. Here's the median soil test K, again 144, above the critical level. So our median, so we're still, even though we're going down, and as you can see, these samples are dropping, we're still above the critical level on average. Looking at the distribution around the state and the current level, you can see the same region here. The lowest values are kind of here in this part of the state. We're solid here. Again, remember, we're talking about 275, 250, 275 would be 100% sufficient. So we're solid in the west. We start getting a little bit lower over here, but we're still in 80% sufficiency. Looking at the Nugis map, again, you can see those hot spots and trends around the country in terms of nutrient enrichment or depletion with potassium. Zooming in on Oklahoma, much darker than our phosphorus map. Again, that kind of follows what we're seeing with the soil test numbers. We can zoom in on some counties again. We'll look at Grant and Texas County again, but let's jump over here in the eastern part of the state and look at one of these dark reds. Let's go with Muskogee County and see what's going on over there. Again, Texas County, same story we see. It's animal nutrients, not putting out nearly as much potassium fertilizer as they do phosphorus, but again, pretty consistent crop removal numbers up through 2016. Grant County, kind of the same story, increasing crop removal, resulting in a more negative potassium balance, just like the phosphorus. And then what's going on here is it seems like something in Muskogee County, they just quit putting out potassium back around 2000. I guess when the price got so high, they just quit applying it, and they've continued to remove. And so we've seen clearly some depletion going on there based on the soil test data. And so again, zooming in on these soil test values, these are the 2017 data. And so these are the ones that are matching what we're looking at on Nugis in terms of strong to moderate depletion, enrichment here, very high soil test K, very high soil test K here, and then 160, which is the index. So again, probably about 85% sufficient. Jump forward to the current data. Again, I think this is probably a sampling thing. I don't think that's a real change. I think that has more to do, that's too big of a change. That's not real for me. That's more samples going here, more samples going there, different labs involved here. You know, that's a lab thing that's going on there in Grant County. Here, not much change, even though we're showing strong depletion or a strong negative potassium balance, not much change in soil tests. But again, you know, like we talked yesterday, that potassium is tricky. There's just a lot of dynamics in play with the potassium soil test that affect those numbers. And so when we're just looking at, you know, we're looking at a 5-year summary here, could be a lot of annual fluctuation. I can't get that from this survey, so I don't know for sure, but that's one of the things we want to do is go back and begin to look at these annually and see if we can figure out some of these changes. The big change here is Muskogee dropped 20 pounds in 5 years on the average soil test. And again, like I said, that variability is there in K, so we have to be careful talking about this, but relatively speaking, that's a pretty significant drop. You know, another calculation, I mentioned we can do nutrient balance and removal to use ratio. The removal to use ratio in 2016 was 9.7. So for every pound of potassium that went out in Muskogee County, 9.7 pounds were taken out of the field. And so that is a pretty significant racial difference. Now, a lot of them are, 1.2, 1.4 when you get in kind of a balanced situation. This is extremely unbalanced in terms of potassium. So whatever's going on over there, we're on our way toward possibly some issues. And so to summarize, what we can say about Oklahoma is that we're depleting soil test P and K. Hasn't been a problem yet in K because we started so high, but we're seeing practice-related trends in terms of increasing crop yields and crop distribution changes and crop type changes and better varieties. And so we're seeing that removal number go up. At some point, we're going to get in a situation where we're going to be able to more consistently see responses to potassium fertilizer, I think. And the P, we just keep going down and down in soil test P. So going forward with this, like I said, this is just something I wanted to do to see what I could learn about soil fertility. And what I see is an opportunity to really get my head around what's going on. And so I'm going to go back and look at all these state lab reports. I'm going to get the raw data, and I'm going to look at these on an annual basis and begin to construct some of those categorical shift figures that I can do with the IPNI survey. I'm going to do that at the state level for Oklahoma by county. I'm going to put together an updated NUGIS database. All these crop removal, acreages, fertilizer data, fertilizer use, all this is available. And so I'm going to put some of that together. I'm going to try to work with TFI and get them to do it for me. If not, I'll probably just hire somebody just to compile those data and put all that together. But I'd like to see, we can speculate what those trends have continued to do based on the current soil test data, but it would be nice to see in terms of understanding the influence of things like, average yield, fertilizer use, crop changes, how is that relating to what we're seeing happen in the soil and our fertilizer management practices. And then we can be a little more confident what we need to do from a recommendation standpoint and from our extension work in terms of information that we need to get out to the producers. So with that wraps up what I had there. Again, just kind of a snapshot of data that's available and some ideas of things that we want to do with it. I'll take any questions anybody might have. No questions?
Mike, you don't have any questions? No, I have one. Okay. You say in the future, like for Grant County, where I'm at, I think some of your correlations would be in that one time frame, we started doing more double crop. We started doing other things, so maybe that's why.
Sure.
So is your studies going to start trying to throw that in there too.
That's exactly the answers that I'm looking for, because that makes perfect sense. You know, is that removal as you're throwing in that second crop, probably not fertilizing the second crop, then that's just that much more removal coming off of there. The thing is though, you know, Oklahoma Ag Statistics, I'm not sure how they count double crop. I don't know if their counts of double crop acres are very accurate at this point, because it is kind of new. Josh Lofton was telling me something about the way they count double crop acres, because I was trying to figure out, you know, what we've got in terms of double crop beans, corn, sorghum, a lot of stuff Josh working with, and it's hard to track those down. But yeah, that's a rabbit we're going to chase. See if we can make some sense out of some of this.
Then some of them here, we have the crop failures where
Yeah.
farmers poured on money, so where they.
You can see that. You can go back through those, you know, from 87 to 16. You can see those, you know, those big drought years in 9 and 10, you know, where the fertilizer was up, the yield was way down, and the next year the yield and the fertilizer were down, and then all of a sudden the yield starts coming back up a little bit. But yeah, you can pick that stuff out historically. Yes, sir. Yeah, different labs handle precision sampling differently. Most of them submitted the individual grid sample number. It came in as its own soil test value. And so, you know, whether that's right or not, I don't know, but, you know, so for the IPNI soil test summary, those came in, most of them sent those individually, because that's how they were entered in their system. Sure. Well, and that is a disclaimer. If you went, okay, yeah, he's asking about how grid samples were handled in the IPNI summary, and you heard my answer, and his response was that that's going to skew the data, and that's absolutely right. And so that's, you know, one of the caveats that, you know, or disclaimers that we make is that you have to understand, you know, how the data is coming in and what it means. And again, you know, these are big snapshots in time. At the state level, it's a little easier to deal with, you know, because we know what we've got, and these data are probably skewed because the better farmers are soil sampling, you know, and so it's probably painting a bit more optimistic picture than reality. You know, we saw a big surge after when the fertilizer prices, you know, went through the roof in around 7, 8. We saw a big surge in samples from everybody, and then over the years where they weren't putting out potash for 3-4 years, guys laid off, you know, potash, and so we saw again they kept testing, you know, watching those numbers, and then, you know, right after the drought there was more testing, wanting to see if there was any residual nutrient there. So, you know, you get those fluxes in the types of farmers that are coming in with samples too. But yeah, you're right. There's a lot of, I mean, it's a model basically, so there are assumptions written into that.
More about the source of the data. You said you excluded like home and garden stuff.
That's right.
Ag samples, are you able to tell us if it's a row crop, cereal crop, or forage crop?
We don't collect those data on IPNI. I suppose Highland's got that data because it's written, you know, when you submit your sample. So at the state level, yes, we'd know what that crop was, but at the national level, no.
Then another small view, I guess, would be diagnostic testing, when we're trying to figure out the problem.
True, those would probably be included, but I don't know that they'd be an influential amount. You know, you figure if we got, you know, 40,000 samples in 2020 from Oklahoma, you know, how many of those are diagnostic? But you're right. It's a good observation.
Any other questions?
All right, appreciate it.
Last speaker of the session before a short break will be Dr. Lofton. Everybody already knows Josh. So, Josh, come visit with us about your soybean. No, you have to stand up here. Don't make David mad. David Deacon, you're going to have to be prepared. All right.
Responsibility for me to do. There we go. Hey, how's everybody doing today? Do we need to get up a 7th inning stretch, huh? Mike's the only one that laughed. You guys are going to leave Mike as the only one that laughed at that? Okay, so anyway, so we're going to move on, and Brian talked about nutrient cycling, and this group is going to talk a lot about nutrient cycling. I had to check the agenda because I'm not going to talk a lot about nutrient cycling. But what we are going to talk about is public service announcement. This is going to be a big thing, and it was kind of interesting because I told Brian what I wanted to talk about a couple of months ago, and then I kind of forgot what we were going to talk about. So I went back, and as I was putting this together, talking about soybean nodulation, I went back and looked at some of my old data and come to find out that my first winter crop school back in the state of Oklahoma was 2015, and guess what I talked about? Soybean nodulation. So 8 years later, we're back. Then it was talking a lot more theoretical about things. We got a lot of data. Being cropping systems and working a lot with crop rotation in soybeans specifically, like nodulation and inoculation has kind of been an underlying issue that we've always wanted to address, and it's something that we always think about. Even more critical in times like these, because how many people had a great looking soybean crop this last year? Dakota had one. He's the only one in the state. Josh also had a great looking soybean crop. So if you want to know how to grow soybeans, Dakota and Josh will be out in the foyer area after this talk. But when we go through these periods of really poor systems, we start really evaluating what we're spending our money on. Are we actually getting a return on investment on some of the inputs that we're putting on? And it's actually a good thing to kind of evaluate, not only in bad times, but in good times. Are we actually spending money on something that's going to get us a return? And inoculum or nodulation and fixation on soybeans is something that always kind of gets brought up. So when we talk about it in general, start talking high-level theoretics, going back to the classroom, we have a need for rhizobium in our systems, okay? We are reliant on those soybeans being nitrogen fixers. We need those things to be nitrogen fixers. And the big critical thing is when we look at the bacteria that creates that symbiotic relationship, in our systems, that bacterium is not native, okay? If you look at where soybeans were developed and originated, if you look at those climate, if you look at the soils that are associated with those systems over in China, over in Korea, over in Thailand, our soils and our environment are not like those areas, okay? So when we bring that bacteria or when we bring that plant associated with that bacteria in, and we bring that bacterium to help that plant, we see that they are not native and they have a hard time outcompeting the native population of our soils, okay? Our bacteria is well adjusted to our conditions, and therefore that bacterium has a hard time. In addition, unlike some areas of the United States, like let's say the Midwest, the Corn Belt, Eastern Seaboard, what have you, soybeans are a lot more frequent in that rotation. We're talking maybe every other year kind of situation, where here it can be every third year, fourth year, or maybe, it just gets thrown in when economics suggest it. So we have a long rotation. In addition, I always say that the cost-benefit relationship or ratio is pretty high with inoculum. Compared to some of our other soybean inputs, the cost of the inoculum compared to the potential if you will, the return, whether it be from a yield perspective or an economic perspective, that ratio is typically pretty high, and so we have a lot of value to that. However, if we decide not to go with that inoculum, just going back, we all know what bad inoculum looks like, right? So inactive inoculum that's not actively fixing nitrogen, when you break that thing open, it's going to be kind of brown, gray, even a black color. What we want it to do is be that really, really bright red color. Now, there's 2 times that you can't check for active nodules. When are those 2 times? 2 times. Anybody? Really early in the season, okay, before we really start pumping that need for nitrogen in that soybean plant, we won't activate those nodules. It's still in the process of activating, right? And then after peak flower, as in through pod production, when we're starting to fill those pods, we've kind of diminished the need for the nitrogen. We need all those carbon that we're producing that we would normally filter into those nodules. So we start turning off some of those nodules slowly throughout the season. By about 5.5, 6.5, something like that, we've pretty much shut down all of our nodule production because we don't need that extra nitrogen any longer, okay? So we can't, at the very end of the season, the very beginning of the season, check for nodules because they're almost all gonna look like that. But in season, this is kind of what we're looking at. So when we talk about the need for inoculation or need for nodulation in soybeans, this is probably the biggest thing. And for soybean to be economical in the state of Oklahoma, and really in the Southern Great Plains, or really in any production system, we need that symbiotic nitrogen fixation. Because per bushel of soybeans, we need on the upwards of 4 pounds of nitrogen. So if we're gonna treat a soybean crop like a cotton crop or a corn crop, we're gonna easily outfarm ourselves. We're going to easily have too much nitrogen input to be able to sustain that crop. So we really are reliant on that because we can't be on our 30 bushel soybean crop be putting 100 pounds of nitrogen on that along with all of our other inputs. So when we take a look at how nodulation and inoculation process works, this is going to be really important as we go through. This is the kind of the system that we're looking at. So a kind of a graphical cross section of a root with some root hairs. The plant basically says to itself at a certain point in time, my demand for nitrogen is really picking up and I can't find nitrogen. So what it's going to do is it's going to excrete a hormone into the rhizosphere, that soil right around the root hair, and it's going to activate that nitrogen fixing bacteria to come and form that relationship. That root hair opens up a tube to where the bacterium can go into that tube. It eventually invades the plant cell or the root cells here into the cortex, and then it forms this nodule, this environment, this low oxygen environment that's right in there that those bacterium are actively fixing nitrogen and producing to the plant. So what does the plant provide the bacterium for them to produce nitrogen? Carbon, yeah, some form of carbon and an environment. And the bacterium is going to produce that nitrogen and give it back to the plant. So what happens if we have lots of nitrogen in the soil? It never triggers. This step right here, this first step never happens. Okay? What happens if we put nitrogen out? V4 application, our beans are turning a little yellow. We want to go throw out some urea. What happens when we deactivate nodules? Do they come back? Nope. Once you've deactivated a nodule, it's got to go find that rhizobium again to reactivate a nodule. Okay, so once we kind of shut these things down, we're shutting them down for good. They got to go through this process all over again. So when we take a look at a plant and a root, nice nodulated soybean root here, where you have nodule is very indicative of how you're managing for that relationship. When we inoculate that seed, where is a bulk majority of those nodules going to go? Did somebody say on the root? I hope they didn't say on the root. Well, I hope they did actually, because that is a correct answer, just not the most correct answer. Where are they going to be in this root system? Out here, way out here in the cloud? Where's it going to be? Down? Wes says down. Right here. Right here at the crown. That's where we're getting the bulk majority of our inoculation or our nodules when we inoculate that seed. So when we get nodules, a lot of them out here on these root hairs, these secondary roots, what does that tell us? Yeah, those are bacteria that's native in the soil. Not native, let's not use the word native because it's not native, but it's active in the soil. So we've been able to form that relationship on bacterium that's out in that soil. However, what we find is that soybeans and soybean in environments like Oklahoma, it's not just Oklahoma, it's soybeans in environments like Oklahoma typically need more frequent managed. And I said that the last time, and a lot of people came up and they said, we don't, okay? So I wanted to answer that question. Do soybeans in Oklahoma need more management than we say the Midwest, Iowa, Indiana, Ohio, Michigan, what have you? Okay, so when we take a look at the justification, the theoretics of this, so this is leaf water potential. So basically what we're looking at is how much nitrogen is being fixed when it gets really dry. The further down this axis you get, the more dry you get. And we see a very sharp relationship. The more dry you get, the less likely that relationship is going to be active and it's going to thrive. So we are getting less and less fixation the drier we get. So these last year, let's say last year in August, were we getting a lot of nitrogen fixation? August and September last year? What about the last 3 years compared to the years prior? We probably weren't getting a lot of fixation comparatively per plant, but we didn't need it because our plants weren't that big. Here's just kind of another indication, once again in different environments. If you take a look at kind of this semi-arid, which is kind of what we're in, soil water content, and this is not only that once we get really low soil water content that this relationship doesn't work, that fixation doesn't work, but it also looks at how adapted they are to re-wetting. So we do get quite a bit of a high amount of nitrogen starting to form with minor re-wetting, but it really doesn't stabilize until we get much more wet in that profile. So it does take, once we get that rainfall, once we get everything happening, it does take a while for them to reactivate and reform those relationships. And if we look at some really old data, if it'll click, just looking in free active fixating bacteria, in these conditions, really wet conditions, we significantly drop the amount of nitrogen that we're being able to fix in any given time. Okay, so theoretically, our environment does indicate that not only is the relationship going to be less effective, but potentially the bacterium itself is going to be less viable and less present in those soils. So when we think about Oklahoma, inconsistent rotations is always a big thing. We've thought about that, but we have parts of the state that are more consistent every other year, every third year, something along those lines. I think this is where we kind of get into our issue. These next two ones, hot and dry conditions, these long periods of drought that we have to go through like we've gone the last couple of years, and then really low pH systems. I think that's where we get into issue with soybean inoculum. Is these two conditions. In addition, even though we're hot and dry, in April, a lot of the times some of our soybean fields go underwater for long stretches of time. You get those April showers, those big rainfall events, significant amount of rainfalls, 24, 48 hours it's underwater, and we have issues there. The question then becomes, what about our seed applied chemicals? And how well does inoculum persist in Oklahoma soils? Okay, so I'll pose the question. How many folks here work with growers or growing soybean, actively putting inoculum out every single year? No questions asked. What about really good inoculum? No, you define that. Okay, so when
Liquid or dry?
we're going to get to there, Mike. Don't worry. So when we asked ourselves this question is how we were going to evaluate that. So what we did is we collected soils from all across the state. We took them into the greenhouse. We grew soybeans in a pot. We let them grow all the way to flowering. At flowering, we terminated the above ground growth. We removed all the soil and we counted the active nodules. Okay, so we did that for quite a few soils. When we take a look at where we collected soils from, kind of that general area that produces soybeans in the state of Oklahoma, we collected at least one grower field from all across the state. With the exception of a couple of these counties, we grabbed some of our research station fields whenever we thought we could get a little bit more information on it. And so this is our information. So set this up because it's going to be consistent for the next couple. So this is percent of responses. Okay, so this is just a percent. We had a total number of soils, the percent that we got. Positive response is indicated that when we inoculated the seed, we produced more nodules than when we didn't inoculate the seed. A negative response or a neutral response mean that there was no significant difference. We produced about as many nodules from non-treated seed as we did treated seed, and negative response is where we produced less. Okay, it's good, we didn't ever produce less. However, only a quarter of the time did we actually produce a no difference. A bulk majority, 3/4 of the time, we were significantly better by producing or putting out that inoculum on the soybean seed. Okay? Fantastic. What you're doing, putting out that inoculum, it's worth it. You can go back and tell your growers that data suggests that it's worth it 3/4 of the time, if you will. So what about years since rotation? Is there ever a time, like let's say we're doing soybean on soybean, would you say to put inoculum on those seed? That's where it's actually recommended not to. You know, we do soybeans in successive years. You don't need to put it, you already put it the last year. So we took a look at that. And so we have anywhere from a 1 to 3 years, so this is being successive years to our typical rotation. 4 to 5 years, longer rotation, or greater than 5 are unknown, meaning that at least since the grower had been working that land, they didn't know, they'd never grown soybeans, they didn't remember if anything else had gone previous. So when we take a look at this, the relationship itself, again, this is percent of responses, the relationship itself is pretty consistent. We had a little bit more over here in this 4 to 5 years since than we did the 1 to 3. But what we saw in general is that it didn't matter on years. We always needed it. So we try to correlate it with a lot of different soil parameters. We tried to do growers. Where's it specific? Growers, and it wasn't growers. Was it counties? Wasn't counties. We looked at other things like nitrogen concentration, potassium concentration. We didn't find anything there. We looked at pH, didn't really have a great consistent. Do you know what and I'll get to it here in this next slide, do you know what the big telltale was? What did I say was one of the main factors in whether those bacteria were active or not? Hot and dry. What of our soybean production systems can we consistently say weren't either hot or dry? Maybe hot, but maybe not dry. Irrigated. So our dry land conditions, to go back to your answer, no matter the pH, we almost always found a response. When we weren't irrigating, we almost always had a response. Or not almost always, we 100% did. In our soils we collected. Where we were irrigated, we were about 50-50 split. And I think then it comes to, like you were saying, some of those other aspects. pH, maybe years since last soybean, something along those lines. But our overriding issue is moisture. Okay? Right now, we actually have some of these soils left, and we're wanting to kind of, if you will, incubate those soils and take those soils and wet them for 24 or wet them for a year and then reevaluate this. Can you bring them back, or are they gone forever? I don't know the answer to that yet. But as of right now, we see that our irrigated systems are to where you can start making that evaluation. Do we need to inoculate or not? Because we have found those very, very split. But in non-irrigated systems, we're 100% in need of inoculum, indifferent of years, pH, what have you. Okay? So this was in a greenhouse. This was just counting nodules. This did not have anything to do with yield. So we also wanted to see how it impacted yield. And not only that, but we wanted to get it out of the greenhouse and look at how it did it in a field setting. It's hard to do root counts in a field setting. I promise you, going and taking a backhoe to just count nodules is not something I don't think my crew wants to do very often. So we have to kind of separate those means, but we do want to look and see how this is done in a field setting. And we've done this a couple of different ways. The first one is one of these things we call an omission trial. So this is building on Cody Leonard, some of his master's work that he did with me. This is full season soybeans. So in this omission trial, if you take and you break this in half, so you have this system that says low input, and the bottom it says high input. If you think of those are your checks. That's what we're comparing everything to. Low input basically took all of these factors, so insecticide and fungicide, insecticide by itself, herbicide pre, fertility pre, inoculation, foliar fertilizer, foliar fungicide, R2 nitrogen. It didn't put any of those out in the low input. Everything else was maintained. But in the low input check, we didn't put anything. In the high input check, we put everything. So we put insecticide and fungicide out, herbicide, fertility, inoculum, foliar fertilizer, foliar fungicide, and R2 nitrogen. And then what we can do is we can play with those factors and we can add them in the low one, or we can take them out in the high one. And basically what we can see then is how impactful that one factor is in a high input system and a low input system by just moving those toggles around, if you will. So what I will for the premise of this presentation, highlighted the inoculum, and basically what we've seen, or what we did see over the last several years, or 18 through 20, is that, and the asterisks are significant differences, is that in our low input system, adding inoculum to that system always improved yield compared to the low input check. So we were always getting a significant yield response compared to the low input check. And it was fairly consistent as well in the high input system, to where we removed the inoculum, that we did significantly decrease yield when we didn't have that inoculum into the seed. With the exception of this last year, it did decrease yield, just not significantly. So we did see that response, it just did not produce enough significant results. There's a lot of information to kind of glean from this, but that's the one we want to take from today, is that inoculum, low input system, high input system, we're getting value from it indifferent. So this goes back into your thing, Mike, and I asked, what about all sources? Are all sources created equal? Is an inoculum an inoculum an inoculum? Nobody wants to venture to guess that one? It'd be a no? Mike, I'm glad you brought that up. I'm going to just have you sit up here with me next year, and you're just going to help go through that. And I think that's an important point to kind of gather and grasp, is that this is a company that sells inoculum. This is all the inoculum. This isn't actually even all the inoculum they sold. This is just what I could capture in a screenshot of the inoculum that they have. So yeah, they do have Brady Rhizobium japonicum, which is what you're going to put on soybean. But if you look there, that's basically all that it goes on. Where if you're doing things like peanuts, alfalfa, maybe you're doing cover crops, so you're doing maybe some dry beans or some chickpeas or something, maybe you got clover with your cover crop mix, those are different, okay? So they all have to be handled different. If you got cover crops, you're selling cover crop seed and you want to inoculate those legumes, that's a different inoculum than just the soybean. We can't just throw the soybean inoculum on that seed and call it good. That's not how that works. So we do have a lot of variability. Okay, so let's say we grab the right inoculum source. We grab the soybean inoculum. Are they now all created equal? No? Venture to say what they're not created equal for. I'm glad you brought that up, because we'll get to that here in a minute. There are a couple of other things that are coming down the pipe that I think are really interesting. Some research has suggested that we have stress-inducing strains of Brady's Rhizobium japonicum. So ones that are more apt to withstand large amounts of stress. So some of those inoculum that can go in maybe these hot, dry conditions and persist and stay in that soil. That is something that is coming down. There's a lot of information talking about level of inoculum, and we'll talk about that, of not only producing more consistent results, but also having those results stay longer. There is some indication that given some conditions in season, our soybean plants shut down our inoculum or our nodules too early in the season. Okay, so when we take a look at type, and this goes back to what y'all were talking about on different types. So we have it's the same inoculum, same company, it's just in dry and liquid. Okay, and who here has heard of these full and double rate inoculum? Putting on 2x rates. Okay, when I went out to the Panhandle, they do this. Western Kansas basically just does this. Okay, and they say because the environment's so inconducive to that nodule forming that you need more bacteria in that system to just get the nodules you need. So we wanted to test that. So this is at the Bixby Research Station, Eastern Oklahoma, Tulsa County. Great moisture, irrigated trial, did great. Non-treated here, did pretty good, actually did a lot better than I thought, but basically everything indifferent of double or full rate out-competed. We did have an issue here. What do you think was our issue here? We had a lower average on our dry single rate application. Say what you said again earlier. It wasn't applied correctly. We had bad application on that one. We didn't get good stick on there. When we planted these plots, I went and looked at the bin, and most of my inoculum was still in the bin. This was dry, stuck to the seed, or liquid on the seed. That's what we looked at, okay? So we didn't get good stick to the seed on this. The double dry rate actually made up for it. So we were able to compensate the fact that we didn't get a good stick on that seed by putting that double rate out. When we take a look at Perkins, so think of Perkins, just down the road here. Dry conditions, sandier soil, not conducive to inoculation, correct? So this is when maybe this full or this double rate will actually work for us, and it did. So what we did is if you compare our double and our full rate, basically everything did a little bit better than the check. We see this is the percent of the check, so in between a 7 to 13% increase. But then when we do our double in this environment, we did see a substantial increase, not only the check, but sometimes over that single rate application. So there is some value potentially in these environments to doing those 2x application rates, and it really just is going to depend on the source. Again, we got a better on our 2x on the dry than we did the liquid, but we still got a pretty good bump on our liquid. It just wasn't significant. Okay, so handling inoculum. This is where I think we run into some of our issue. Where do you store your inoculum? On the dashboard. Okay, everybody bow their head. We're going to pray for that inoculum because it is no longer with us in this world. Okay, that's the issue, because what is inoculum? It's a living organism, okay? When we talk about our living organism, we talk about all the things that Brian has said on soil samples and everything going on. We should know better. But so we did a little test. I looked at inoculum storage. So we did it in a cold room, in our cold room, which is where you're supposed to store inoculum, right? Not freezing, but cool. I think it's anything under 71 degrees consistently is what it says on most labels. AC office, so it just sat in my office, okay? And then I put it out in our shed. So it's still dark, because it doesn't like light either, but it is still dark, but it's hot, okay? And this is the viability, so this is how long we left it in there, 24 hours, 7 days, 14 days, 21 days, and 28 days. Then we grew it in the pot and counted the nodules. And this is what we found, number of nodules. When we left it in there 24 hours, no harm, no foul. You forgot it in the truck, it's okay. Get it in the cool room as soon as you can. By 7 days, we've started to degrade that, and by 14 days, basically, we're not going to get a good nodulation on that soybean plant. The AC office maintained all the way through 14 days, but by 21 days, we started seeing that difference, that AC office right at that upper edge of where we're supposed to maintain and store inoculum. It did degrade over time. Most people don't store their inoculum for 28 days. Maybe it's a season. Maybe it's a couple seasons, what have you. Seed also isn't stored in a cooled environment most of the time. It is stored potentially in that shed. So it is one of those things we got to start thinking about on saying, oh, well, my inoculum didn't work. Well, when did you put it on the seed? 2 months ago. Where was the seed held? In my shed. There it is. Okay? What we want to do is inoculate, coat this seed as close to it going into the ground as possible. If it can be done the day of, let's do it the day of. Otherwise, we need to store it in as cool of environment as we possibly can. The other thing we get asked, the last thing we're going to touch base on, is is seed treatment fungicide bad for inoculum? No. Any questions? We've never seen it. I've run this in Louisiana. I've run this in Oklahoma. We get this asked all the time. Every time a new seed treatment comes out, is it bad? Actually, it actually kind of helps. Adding the inoculum and the fungicide in there actually improves our yield. So even when fungicide wasn't important, so we got our single crop, inoculum wasn't significantly improved yield compared to the check. In our double crop, it really improves yield, but our fungicide doesn't improve. But indifferent, both times, seed treatment plus inoculum improved yield. Okay? All right, some take-homes in and out. In most of our soybean systems in Oklahoma, Southern Great Plains, I think you can say, adding inoculum, it's going to benefit most of the time. Okay? Because we have those hot and dry conditions, prolonged droughts, maybe some cooler conditions, it is one of those things that we probably can see a benefit on most years. And the biggest thing is it gets more consistency. That's what we want. We don't want our soybeans to have one more issue that we have to worry about. It's a cheap safety net for consistency. And if growers like one thing, it's definitely consistency. If I've known one thing coming back to Oklahoma, it's consistency, consistency, consistency. So longer rotations, we need more, or we potentially have an increased benefit from adding inoculum. The later we go, the more valuable it is because that soil is hotter and drier whenever we plant that, so that relationship gets a lot less conducive. Our higher yielding environments, we definitely need to make sure that we have some in. And then after big challenging conditions, drought, major floods, what have you, we need to be looking at that inoculum as an input source. Some literature on some of those graphs, and then some contacts. Twitter or X, whatever you call it. Instagram, we have an Instagram thing. YouTube, go some videos. Brian, do we have time for questions? Questions? Mike?
I planted some early beans in 1st May.
Yep.
Cut my wheat, first part of July. I still have that inoculum that I used earlier. Is it any good?
Where'd you store it?
Various places.
Okay, so is it any good? Various answers.
I mean, well,
If
right, is that early season bought inoculum still going to be good 70 days later after I purchase it?
Yeah, I think if good storage, I think that inoculum is going to last. So if you've done everything right, you stored it in a cool environment, kept the light off of it, et cetera, et cetera, et cetera, you're going to be pretty good. I mean, we've done inoculum. Hold. We've done that's what you were going for, Brian. If you've stored inoculum, if you put it on early season beans, they went out, you planted them, now you're going to late season double crop beans, is that inoculum still good within a year? I can't see a reason, if not, as long as it was stored properly. No, he was saying that you treated seed early, you planted that seed, now you're coming in with double crop, you still got some inoculum left over, you stored it in a cool room throughout. Is that still good to use? You need to buy some more, right? And I think you're still pretty good on that. We used inoculum throughout the year in the program without any issue. Brian. I will not do a riddle today. You don't have to. So Brian posed this riddle of if you have an air seeder that's going for 4 days on a bag of seed, do you have to unload and retreat? I mean, theoretically, you have some maybe potential for decreased nodulation, but there are other ways for us to get this out in the system. We have methods to where we've looked at foliar applying inoculum, we've looked at squirting it on to the ground right after germination, and those have varying levels of success, but you have a means to get that out there.
But he's probably getting at that temperature in that bin, it's going to get up to about 130, 140 degrees.
Yeah, so you go back to this, and we're still here at 7 days, we're losing it, but we're not there yet. If you're planting 14 days later, you can potentially run into an issue. This was in the middle of summer. What was that, Mike?
Keeping it that higher temperature?
Well, see, this is the middle of the summer, and we see it at 7 days. We're starting to lose it, but it's not gone yet.
But if you're in an enclosed environment, your temperature's gonna be another 20 degrees higher than what it would be out in the open. Because you're inside a closed bin.
I still think you're, so going again on if in that closed environment, the temperature's really spiking, what have you, I still think you're okay for short term. What we don't want to do is store it, going back to your first question, what we don't want to do is store it from the full season soybean production to the late season soybean production in the dash of your car. We don't want to have seeds still sitting in the air seeder from April and try to plant it in June without retreating it. That's the kind of things we don't want to do. Now, 4 days, it takes us 4 days to go through all the seed and the seed's following around the air seeder. I don't think you're having an issue. We're talking about much longer of a scale here. Yes, sir. So there are forms that, what was that? Oh, repeat, sorry. So if I heard this correctly, there are some indications of inoculum going on other non-leguminous crops like corn, correct? So that's if you kind of remember back to the first couple of slides where we talked about the process of soybeans going through that nodulation process to where we have the invasion of that root cell, that's unique to legumes and other infixing within that family. We do have other technologies that are coming around to where they don't invade the intercellular space, but they might invade the very, very edges of the root or have that nice connection within the rhizosphere. So we're talking about a couple of micron difference between the plant and the soil, and it's fixing nitrogen just freely, so the plant isn't producing that environment, but it might be sharing those resources, and it does potentially fix some nitrogen for some of those other crops. So there is some validity to that. It's just not the same process. So Mike, we can talk in a minute. Brian's saying we got to wrap it up, so just come up and see me. I'll be more than happy to talk. We do have a fact sheet on this. If you go look up soybean inoculation and nodulation, it's on the fact sheet website.